Hello and welcome to Aliathon's 100G Transponder and Muxponder demonstration video. My name is Alan McDade and I'm responsible for sales and marketing here at Aliathon. Before I take you through the demonstration, I'll first walk you through the hardware setup and the FPGA architecture. The diagram on your screen now shows the hardware setup when in Muxponder mode. On the client side we have the JDSU ONT601, which supplies both the STM64 and 10G clients. These clients are delivered from the tester over a set of optical fibers to SFP Plus modules, which are housed in two Hi-Tech Global SFP Plus cards. These cards are then connected to the Virtex 7 platform via Samtec bullseye cables. The entire Muxponder, which I will describe in more detail later, resides in the Virtex 7 485T device on the Xilinx development card. On the line side we have the JDSU ONT503, which is configured in OTU4 mode and are also using JDSU's own electrical CFP module. This module is connected to the Virtex 7 platform via another set of Samtec bullseye cables. The diagram on your screen now shows the architecture of our Muxponder. The client side is represented by two 10G SFP Plus client connections, one 10G and the other STM64. Each connection has an independent reference clock input, which is supplied by an external VCXO, enabling independent TX frequencies. To make the demo easier on the eye, we've chosen the two most popular client rates used in the comms network today, and in the case of STM64, the most challenging to map. This allows us to use a single piece of test equipment to generate all the client signals. We do, however, route each of these signals to 5 ports of the mapper block, which allows us to 100% fill the ODU4 payload. This variant of the 10G client to ODU2 mapping core provides support for 10G Ethernet and STM64. The core maps these clients using the ITU-defined containers. The 10 ODU2s from the client mapper connect to Aliathon's ODU2 to ODU4 mapping core, which in turn forms a single ODU4 and passes this to the OTU4 framer. The ODU4 mapping core uses the standard GMP mapping technique of 1.25 GHz time slots to multiplex the clients into the ODU4 payload. The OTU4 framer provides standard OTU4 framing, scrambling, detection of parity errors, and drops the overhead. The framer connects to our standard GFEC encoder-decoder block, which delivers 6 dBs of gain while consuming 7% of the frame overhead. The core provides full stats, which are corrected, uncorrected bits, blocks, and codes. Now, while this demo uses a standard GFEC core, Aliathon can also provide an enhanced FEC core, which delivers 9.35 dBs of gain for 7% frame overhead. On the OTU4 side, the design implements an OTL 4.10 interface, which supports up to 1024 bits of skew. This incorporates 10 11.18 GHz SerDes with individual lane framing, skew adjustment, and reordering. Finally, we have a microblaze-based subsystem, which allows us to control and monitor the design via a Windows GUI. The diagram on your screen now shows the hardware setup when in transponder mode. On the Ethernet side, we have the JDSU ONT503, which is configured in 100G mode and are using JDSU's own electrical CFP module. This module is then connected to the Virtex 7 platform via a set of Samtec bullseye cables. The entire transponder, which I'll describe in more detail later, resides in the Virtex 7 485T device on the Xilinx development card. On the line side, we have another 503, this time configured in OTU4 mode, and again using JDSU's own electrical CFP module. This module is again connected to the Virtex 7 platform via a set of Samtec bullseye cables. The diagram on your screen now shows the architecture of our transponder. On the Ethernet side, we have 10.3125 gig SerDes, which are used to implement a Cowie interface. After bit demuxing, the individual lanes are 66B deframed, deskewed, and reordered to produce an interface that is 10 aligned and contiguous 66B code words wide. The associated PCS and MAC blocks provide code word unpacking, frame delineation, and CRC checking. The 100 gig Ethernet to ODU4 block bit transparently maps the 66B code words into an ODU4 payload for transport by the OTU4 framer, and this is done using the generic mapping procedure, GMP. The OTU4 core provides standard G709 framing, scrambling, detection of parity errors, and add drops the overhead. The framer connects to our standard GFEC encoder-decoder block, which delivers 6 dBs of gain while consuming 7% of the frame overhead. The core provides full stats, which are corrected and uncorrected bits, blocks, and codes. Now, while this demo uses a standard GFEC core, Aliathon can also provide an enhanced FEC core, which delivers 9.35 dBs of gain for 7% frame overhead. On the OTU4 side, the design implements an OTL 4.10 interface, which supports 1024 bits of skew. This incorporates 10 11.18 gig SerDes with individual lane framing, skew adjustments, and reordering. Finally, we have a microblaze-based subsystem, which allows us to control and monitor our design via the Windows GUI. Okay, let's move on now with our Muxponder demonstration. We'll start by launching the Aliathon control and status interface and configuring our design in Muxponder mode. The control and status interface has 4 main tabs, and that allows us to report back the status and errors at the OTL, the OTN, the ODU4 and ODU2 layers. It's worth pointing out that the Aliathon design is monitoring all 10 client signals, all 10 ODU2s within our design. The reason why only one here is active or valid is that the JDSU, the 100 gig JDSU, will only generate, transmit and receive one 10 gig client within a 100 gig payload. So moving on to our test equipment. And we'll be using our STM64 client tester and the 100 gig OTU4 tester. If we start from the OTU4 side and examine the physical interface, we can see that the bit rate is as expected, OTU4, and we have a small frequency offset. This is due to a slight difference between the transmit reference clock on the Virtex 7 card and the receive reference clock in the JDSU test equipment. Moving down to the OTL layer, I explained during the FPGA architecture that the OTL core has the ability to dynamically reorder the lanes, and we can examine this by using the JDSU box to reorder them on the way in. So if we move this down, we can see the expected alarms and then the design recovering. We can also see the same thing in the Aliathon status interface. Moving on to Skew, the OTL core provides support for up to 1024 bits of Skew, matching the ITU standard. We can demonstrate this by injecting Skew on a lane-by-lane basis, and again watching as the design compensates. And again, we can see the same thing through the Aliathon GUI. However, this time we can also see which lanes are being skewed. Moving on to the OTN layer, we can inject errors and alarms at the OTU and ODU4 layer and watch again as the design compensates. If we start with an ODU AIS, we can see the expected alarm signals generated on both sides of the link. And if we look at the Aliathon GUI, we can see our design correctly reporting these back. Moving on to errors, we can inject uncorrectable and correctable FEC errors, and again using the Aliathon GUI, watch these being reported. If we start with uncorrectable, we can see the GUI report these back and show a count of the number of errors we've seen. And the same for correctable. Moving on now to the ODU layer 1. Again, we can inject alarms and errors. This time we'll go with an OOF alarm, again set to continuous, and watch as that's reported back on both sides of the link. And again, looking at the Aliathon GUI, we can see the appropriate BIP and BEI errors. So finally, moving all the way down to the SDH layer, we can now transmit and receive errors and alarms from both sides of the link and watch as they ripple through our design. If I start with the 100 gig side and insert a LOF error, we can see that reported on the 10 gig side. Similarly, if I inject a B1 error, again, we see that reported on the 10 gig side. If I move now to the other side of the link, and insert an MSAIS alarm. We can see that reported back on the 100 gig side. And finally, if I show a B3 error, again, that's properly flagged up on the 100 gig side. Okay, earlier I explained that although we have two independent client signals, we replicate both of those signals 5 times to entirely fill the ODU4 payload. We'll now move on to inspect another set of time slots and therefore another copy of the SDH client signal. So at the moment, the tester is set up to examine time slots 1, 11, 21, etc., etc. We'll change this to another set of time slots that contains another copy of the STM64 client signal. So this time we've chosen time slots 3, 13, 23, etc., etc. Note that we do have some alarms on the 10 gig SDH tester, and that's because we only have 2 client signals. For the purpose of demonstration today, we've kept this simple and replicated those through. For a real world design, we would simply hook up more independently clocked transceivers and bring out the rest of those transmitted client signals. Because of the replication, though, in the transmit direction, we can still send errors from the STM64 side and see those rippling through to the 100 gig box. So, for example, if I send a B3, we can see this correctly reported back on the 100 gig side. So I'll now switch back to the default time slots and the original copy of the STM64 client signal. We'll now move on and examine some even time slots which contain the 10 gig Ethernet client signal. So if I minimize the STM64 client signal and bring up the 10 gig E box. Before I move on and examine these time slots, I mentioned earlier that the JDSU box is only capable of producing, generating a single 10 gig client within a 100 gig payload. It's also only able to produce an STM64 client, not 10 gig E at this time. So we'll use some other markers to identify the 10 gig E client, but I'll also enable a loopback at the OTL layer, which allows us to loop back the transmitted 10 gig E client to the receive side of the 10 gig E test box. And as I do this, we see the 10 gig E tester showing all green. So moving on to the 100 gig side, we'll now examine some time slots containing a 10 gig E client signal. One of the ways we can use to identify the 10 gig E client is to look at the nominal payload rate and the effective payload offset. So to compare this, I first brought up the STM64 client signal. So we can see here that the effective payload rate of 10.037 gigabits per second, or ODU2, and a very small payload offset, so it's correctly transmitting and receiving the STM64 client. If I then look at a set of time slots containing the 10GE client, we can inspect the stuffing and see that the effective payload rate has jumped to 10.399 gigabits per second, or ODU2E, and that the payload offset is large, as expected. We can also see that the SDH layer is unhappy because we're now receiving an ODU2 that contains a 10GE and not the STM64 that the box is expecting. If we move on to the 10GE client side, we can inject a frequency offset and watch the effect that has on the payload on the 100G side. And we can see the payload jump as the frequency offset takes hold. Finally, we will inspect another set of time slots to look at another version of the 10GE client signal. So again, going to OTN config, we'll select another set of even time slots. So this time choosing 8, 18, 28, etc., etc. And again, if we check the stuffing tab, we can see the ODU2E effective payload rate and the large payload offset. Finally, we can also inject the frequency offset and then watch as the payload rate jumps accordingly. That concludes our 100G Muxponder demonstration. Let's move on now to our transponder demonstration. We'll start by again launching the Aliathon GUI, and this time configuring our design in transponder mode. Again, similar to the Muxponder GUI, we have 4 tabs, OTL, OTN, and ODU4. This time the ODU2 tab is replaced by a COWI tab, where we can see the status of the COWI interface, and we can look at the stats from the 2 Ethernet ARM1 monitors in both the ingress and egress directions. So if we bring up our test kits and start by looking at the OTU4 side, we can inspect the OTL interface, and similar to the demonstration on Muxponder, we can vary the lane mappings and watch as the design will successfully reorder. And again, we can see that on the Aliathon GUI. Moving on to lane skew. As I mentioned before, the OTL core supports up to 1024 bits of skew. And we can demonstrate this by injecting skew on a lane by lane basis. Okay, moving on to the OTN layer then. We can inject alarms and errors, and again watch those ripple through our design. If we start with alarms and inject an ODU AIS, we can watch as that is reported and rippled through our design. That's in both the 100G Ethernet tester and on the Aliathon GUI. If we move on to errors, we can inject uncorrectable and correctable FEC errors and watch as the Aliathon status interface reports those back via the microblaze. Finally, moving on to the MAC IP layer, we can send and receive errors in both directions. If we start from the 100G Ethernet side, we can send an FCS error and watch as that's reported on the 100G side. If we move in the other direction and send a runt, again we can see this reflected on the 100G Ethernet side. That concludes our 100G transponder demo. That's the end of our demonstration video today, and we certainly hope you found it useful. For more information about Aliathon's products and services, please go to aliathon.com, and to contact us, again go to aliathon.com and click on the Contact Us tab at the top of the page. Thanks for watching.